For centuries, we've gazed upward, wondering if we'll ever reach those distant lights. According to conventional wisdom, the answer is a resounding no, at least not anytime soon. The universe's ultimate speed limit, 299,792,458 meters per second, stands like an immovable barrier between us and the vast cosmic ocean. But what if everything we thought we knew about this universal speed limit was incomplete? What if Einstein, the very man who cemented the speed limit in our scientific understanding, also left us breadcrumbs to surpass it? The year was 1905. A 26-year-old patent clerk submitted a paper that would forever change our understanding of the universe. Albert Einstein's special theory of relativity gave us the famous equation E=mc², establishing the speed of light as the universe's ultimate speed limit. This revolutionary idea presented a cosmic paradox. As an object approaches the speed of light, its mass increases toward infinity, requiring infinite energy to push it further. Case closed, right? Not exactly. While Einstein did establish this limit, hidden within the complex mathematics of his later work, his general theory of relativity lay the theoretical seeds for potential loopholes in this cosmic speed restriction. Einstein's equations revealed something extraordinary. Space-time itself is flexible, malleable, subject to warping and bending. While no object can accelerate through space-time faster than light, space-time itself has no such restriction. This subtle but profound distinction would later inspire theoretical concepts like wormholes and warp drives. Einstein never set out to help us break the light barrier, yet his mathematical framework inadvertently provided the theoretical foundation for possible methods to circumvent it. Consider this. When you drive from New York to Los Angeles, you're moving through space at perhaps 70 miles per hour. But what if, instead of driving faster, you could fold the map, bringing Los Angeles and New York temporarily closer together? You wouldn't break any speed limits, but you'd arrive sooner nonetheless. This crude analogy hints at how Einstein's equations might allow us to reach distant stars without technically breaking the universal speed limit, not by moving faster through space, but by manipulating space itself. The brilliant physicist John Wheeler once said, "Space-time tells matter how to move. Matter tells space-time how to curve." This profound insight from Einstein's work suggests that with sufficient energy and the right technology, we might create shortcuts through the cosmic fabric. Theoretical constructs like the Alcubierre drive propose creating a bubble of space-time that contracts in front and expands behind, essentially surfing on a wave of space-time while remaining stationary within. The bubble, the ship itself, never exceeds light speed locally, yet could effectively travel faster than light from an outside perspective. But why can't we put these ideas into practice? Why aren't we already zipping between star systems? The obstacles are formidable, bordering on the impossible with our current understanding and technology. The energy requirements alone are staggering. Early calculations suggested we would need negative energy equivalent to the mass of Jupiter, a concept that remains largely theoretical. Exotic materials with negative energy density might be required to stabilize wormholes or create warp fields, yet we have only the faintest evidence that such materials could exist. The quantum realm adds another layer of complexity. At microscopic scales, space-time may not be the smooth continuum Einstein envisioned, but rather a foaming, bubbling quantum soup. Any attempt to manipulate space-time at these scales runs headlong into the unresolved tensions between general relativity and quantum mechanics. We're trying to build a starship using blueprints written in two different languages, neither fully translated into the other. Then there's the engineering challenge, creating and containing the enormous energies required, directing them precisely to warp space-time in the desired configuration, and protecting any passengers from the extreme tidal forces would require technological capabilities centuries beyond our present abilities. Our most advanced particle accelerators and nuclear facilities are like stone tools compared to the technology needed for practical faster-than-light travel. Yet, despite these daunting obstacles, the phrase impossible has a history of yielding to human ingenuity. Consider that just over a century ago, powered flight was considered impossible by many serious scientists. Nuclear energy was deemed impractical. The moon was unreachable. Time and again, the hard wall of impossible has proven to be merely the challenging boundary of not yet possible. Recent theoretical work offers tantalizing glimpses of potential pathways forward. Refinements to the Alcubierre drive concept have dramatically reduced the theoretical energy requirements from absurd to merely extremely challenging. Advances in metamaterials and quantum field theory are providing new insights into how space-time might be influenced through technological means. The discovery of naturally occurring negative energy densities in certain quantum systems hints that perhaps the exotic materials we need aren't entirely beyond our reach. In laboratories around the world, scientists are probing the fundamental nature of space-time itself. Experiments with quantum entanglement reveal spooky action at a distance that seems to transmit information instantaneously, challenging our understanding of locality. Advanced interferometers designed to detect gravitational waves are measuring minuscule distortions in space-time with unprecedented precision, giving us new tools to understand its fundamental properties. Perhaps most exciting are theoretical developments suggesting that quantum mechanics might allow for certain types of information to travel through microscopic wormholes, creating a form of quantum teleportation that could one day lead to practical applications. While teleporting humans remains firmly in the realm of science fiction, these quantum effects hint at deeper structures in space-time that could eventually be harnessed. The engineering challenges remain immense, creating the conditions to manipulate. Space-time would require energy densities and control systems far beyond our current capabilities. However, history teaches us that theoretical understanding often precedes technological application by decades or even centuries. The basic principles of nuclear energy were understood long before the first practical reactor was built. The mathematics of computation existed before the first modern computers. What might the first practical faster-than-light system look like? Perhaps not the grand starships of science fiction, at least not initially. The first applications might be in sending information rather than matter, quantum communication systems that exploit space-time loopholes to transmit data instantaneously across vast distances. Or perhaps tiny probes, quantum-scale devices that could utilize microscopic wormholes to explore distant regions of space without conventional propulsion. The implications of success would be profound, transforming humanity from a planetary species to a truly cosmic civilization. Distant star systems that would take tens of thousands of years to reach at conventional speeds could become accessible within a human lifetime. The vast resources of our solar system would be just the beginning. The galaxy itself would open to exploration and perhaps colonization. Einstein's equations showed us both the barrier and the potential pathways around it. The speed of light remains an insurmountable obstacle for conventional motion through space-time, but perhaps not the final word on our cosmic reach. As we deepen our understanding of quantum gravity, dark energy, and the fundamental structure of space-time itself, new possibilities may emerge that even Einstein couldn't foresee. So when we gaze up at those distant stars, perhaps the correct response isn't resignation at their unreachability, but determination to find the loopholes in the cosmic rulebook. The light barrier stands firm today, but with each theoretical breakthrough and experimental advance, we inch closer to the day when can't becomes can. Einstein showed us the limits of the universe, but perhaps also left us the mathematical keys to transcend them. The journey to faster-than-light travel remains humanity's greatest challenge, a problem that spans physics, engineering, energy production, and materials science. But the greatest journeys begin with the belief that the destination, however distant, is ultimately reachable. We stand today, like the Wright brothers before their first flight, sketching dreams of cosmic travel on the edges of our scientific understanding, knowing that the gap between theory and practice may take generations to cross. Yet, history suggests that the seemingly impossible has a way of becoming routine. The universe has surprised us before with its hidden pathways and unexpected possibilities. Perhaps Einstein's greatest gift wasn't defining the cosmic speed limit, but providing the mathematical framework that might someday allow us to circumvent it, propelling humanity to the stars not by breaking the rules of physics, but by understanding them more deeply than ever before.